Hello and welcome to our today's topic, which is proof by contradiction. Before we get started, we need to know what is a proof. Well, a proof is a logical argument that tries to show that a statement is true. In math and computer science, a proof has to be well thought out and tested before being accepted. Even then, a proof can be discovered to have been wrong. A theorem is a mathematical statement which is proven to be true. We have several types of proofs, but the main ones are direct proof, proof by induction, and proof by contradiction. Indirect proof, or as some like to call it proof by construction, we assume that P is true. P represents a mathematical statement we're trying to prove. And then we use P to show that Q must be true. In proof by induction, we have 3 steps. For n equals to 1, our theorem is true. So if we have some sort of formula, we replace the n in the formula, the unknown variables, with a test number which is 1. So if it works for 1, then we assume it's true for the first step. The next step is to assume that it's true for some integer, which we will call k, and k is an integer which is greater than or equal to 1. And once we suppose that, we try to prove that our theorem is true for every consecutive integer, which is k plus 1. So even if we proved it to be for 2 or for 3, where we wrote that k is equal to one of those integers, it should be true for each consecutive integer. That's where the plus 1 comes from. So we will start off with trying an example using direct proof. So here we have a theorem which says if a and b are consecutive integers, the sum of a plus b must be an odd number. So step 1 is to, in fact, figure out what does this consecutive integer mean. Well, if we assume that a is 1, then b must be 2. So b equals to a plus 1. The next step is to write the sum in a different way. So we are just going to write it using only one unknown variable, which is a. So a plus b, which is a plus 1, in fact, equals to 2a plus 1. And this 2a can be replaced by 2k, k meaning defining any other variable we can use. And so, if we analyze this expression, we get that any integer multiplied by an even number must be even. And if we add 1 to any even number, it becomes odd. So a plus b equals to 2k plus 1 shows that the sum of a plus b is odd. So let's try to test this out. If we assume that a is equal to 1 and a and b are consecutive integers, then b is equal to 2. And if we add those two, 1 plus 2, that equals to 3. And 3 is an odd number because it can be written as 2k plus 1. So multiply by an even number, 1. 1 is multiplied by an even number, from which we get 2, and then we add plus 1 to it, and so we get 3. Therefore this works. QED is what we do when we have proven something. We put the symbol QED. The next example we have is from proof by induction. So we have a theorem which is in fact a formula of the sum of an arithmetic sequence. So s of n, which is a function, is equal to n times 1 plus n over 2. So step 1, in proof by induction, we test out that n is equal to 1. So here we need the sum until 1 should be equal to 1. But we don't know. So 1 times 1 plus 1, that's 2. And 2 over 2 is 1. And 1 times 1 is equal to 1. Therefore, it is true. We can move on to the next step. Step 2, we assume that n equals to k, and k, as we said earlier, is equal to or greater than 1. So the sum of a sequence all until k should be equal to k times 1 plus k over 2. Step 3, this is where most of the calculations happen, and this is where the theorem is proved in this step. So the same way we did the last step, so until all the variables until k plus 1, and again we replace k by k plus 1. So here what we do in fact is we have a similarity here. So this part here is equal to this part. So we just replace this part and put it here. And after this, that's one of the trickiest parts in proof by induction. But after this, all you need is simple algebraic manipulation to prove that these two sides are equal. And once you have proved that these two sides are equal, you have proved that the theorem works for every integer. So we just add here 2 over 2, which is, when you simplify it, equals to 1, but we just want to add these two and give this expression a common denominator. Here we just move these two so you can see easily that k plus 1, k plus 1. And after that, here we multiplied each of these to get this expression. And after further simplification, we get that k plus 1 times k plus 2 is equal to the same expression. If we, of course, multiply this, we will get the same thing. Therefore, it has been proven. So now that we have finished all of these, we will start with proof by contradiction. But before we get into that, we need to know what is a contradiction. A contradiction is the combination of statements, ideas, or features which are opposed to one another. For example, here we have a sign saying no, but when you look close it says yes. So it's contradicting towards one another because we don't know what it's trying to say. It's again same with these signs, stop and arrow implying that we should go in one way. And then here we have a sign which says one way but shows two directions. So in fact, this is how it works. We have a young boy who is in a courtroom and has been convicted of theft. So we need to somehow try to convince the judge that he's not guilty. So the way to prove it, in fact, is by using proof by contradiction. So the question we need to ask is, does the boy have the money he has stolen? Well, if the boy did have the money, let's assume the opposite. If the boy did have the money, if he did steal it, then he would have still had the money and he would have been rich. But he doesn't have the money, he didn't steal it. Therefore, he's innocent. And that is a contradiction. He has proven to be innocent. So let's go through this all over, but in written down steps. Why is the boy innocent? Well, first of all, the boy was accused of stealing money. We want to prove that the boy did not steal the money. So we first assume the boy had stolen the money. But if he did steal the money, he would have had the money with him. But he doesn't. We came to a contradiction. So this is in fact how proof by contradiction works. So these are the steps of proof by contradiction. So we first assume the theorem is false. And then we try to prove the theorem is true, which we have assumed. But then we run into a contradiction. So here we'll do one example. Show that there exists no integers x and y for which 6x plus 9y equal to 1. So here we have an example 1 of proof by contradiction. Show that there exist no integers x and y for which 6x plus 9y equal to 1. Well, the first thing we need to do is that we need to assume the exact opposite. So we assume that there are integers x and y which do make the statement correct, which exist for the statement. So 6x plus 9y equals to 1. So we take this common multiple of these two, so 3 times 2x is equal to 6x, and 3 times 3y is equal to 9y. So we just took the common multiple out. So if x and y are integers, then 2x and 3y must also be integers. So an integer plus an integer must be equal to an integer. But if we again change this to another side, and we get 2x plus 3y equals to 1 over 3. This has been proven because here we have an integer plus an integer equals to a fraction, and that's a contradiction, and that's why this has been proven and it does not work. Therefore, there are no integers x and y for which 6x plus 9y equal to 1. So now we have example 2. Prove that root of 3 is irrational. So as per usual, we assume the opposite. We assume that root of 3 is rational. Rational means that we can write the number as a over b, where a and b are integers, meaning that we can write the number as a fraction. So root of 3 equals to a over b, where a and b are integers, as we already said. And b cannot be equal to 0 because we cannot divide by 0. And a and b is in its simplest form, which means that a and b do not have any common multiples within them. So now we just do simple algebraic calculations. We square root both of the sides by 2. So root of 3 squared equals to a over b squared. We get that 3 equals to a squared over b squared. And after we do cross multiplication, we get that 3b squared equals to a squared. A squared and a must be multiples of 3 because we need to remember all of these a and b are integers, so we cannot have any fractions. So from this, we assume that a equals to 3n. So 3b squared equals to 9n squared. And if we divide both of the sides by 3, we get that b squared equals to 3n squared. B squared and b must be multiples of 3 because again we said that a and b are both integers. So a and b have a common factor of 3 because we said here a and b must be multiples of 3, and b squared and b must be multiples of 3, so they have a common factor. But this is a contradiction because in the beginning we said that a over b is in its simplest form. Therefore, they cannot have any common multiples. And what I mean by that is when we have a over b, and if we assume, for example, that it's equals to 5 over 2, that means it's in its simplest form. But if we write it as 15 over 6, both of them have a common factor, which is 3, so we can write it like this: 3 over 5 times 3 over 2. So this is a common multiple, but we said that a and b is written in its simplest form, so therefore it's a contradiction here. So this has been proven to be true. So root of 3 is in fact irrational. Example 3. Prove by contradiction that the sum of a rational and an irrational number is irrational. So again, we need to assume the opposite, that the sum of these two numbers is rational, meaning that it can be written as a over b. The second step is to denote the irrational number by c, because we can't write it in another way. We can't write it as a fraction, which is made of integers. Then the third step, we need to denote the sum of a rational number and a rational number by d over e. So we just give other integers, but again we write it as a fraction. So a over b, which is our rational number, the first one, is here. And then our irrational number is here, and then the sum is here. So that's how we write it. And then if we just try to find out what is c, like we need to prove either that c is irrational or that c is rational. So c equals to d over e minus a over b. And if we try to write this, try to subtract this, we need to find a common denominator. So we just multiply each of these. We multiply b by d and we multiply a by e, and these two become together multiplied and they become eb. So we in fact managed to write c as a rational number. So we wrote this as a fraction which is rational, and the numbers are simple integers. So we came to a contradiction. Example 4. Prove that there are infinitely many prime numbers. So let's assume that there is a finite number of prime numbers. And let x be the product of all prime numbers. And then let y be equal to x plus 1. Y has no prime factors because there will always be plus 1. So in fact, x is equal to, so we have a prime number which is p1, and then that times p2 times p3 times all the way until some certain prime number, and this is equal to x, and then y is simply x plus 1. So y has no prime factors because there will always be plus 1. So whichever number this is, we need to add plus 1 to it. And so it can never in fact be a prime number, and this is where it all happens, because either y itself is prime or y is not prime and has a factor which is not listed. So if y itself is prime, that means we didn't list it within the x. Or if y is not prime and has a factor not listed inside, then again we didn't list all prime factors. And so if we can't list all prime factors, that means that we have proven this, because there are infinitely many prime numbers. If there was a finite number of prime numbers, we would be able to list all of them or most of them, but since there are infinitely many, we can't. So this is our last question, and it's quite a simple one. Prove that triangle ABC, meaning any triangle, can have no more than one right angle. So again, we assume the opposite. Assume that triangle ABC can have multiple right angles. So angle A plus angle B plus angle C equals to 180 degrees. As we know, the sum of interior angles of a triangle is equal to 180 degrees. So if some angle A is equal to 19 degrees, and angle B is equal to 90 degrees, then angle C should be equal to 0 degrees. But triangles must have 3 angles, so none can be 0 degrees. Therefore, we have proven this statement to be false, and so the triangle ABC cannot have more than one right angle. Thank you for your attention, and these questions were taken from the A-level syllabus of math.